In this chapter, we're going to talk about electrochemistry, which is the process by which we take chemical energy and transfer it into electricity, or vice versa. We can take electricity and transfer it into chemical energy. So electricity and chemistry are intricately related because electrochemistry is the flow of electrons. And where do those electrons come from? They come from different chemicals. So we'll look at some processes by which electrons are moving, which is the whole key to electricity. We'll look specifically in this lecture at a type of cell, which is another term for battery, called a voltaic cell, and the synonym for that is a galvanic cell. And the key to those two types of cells, they're the same thing, is that they produce voltage. So that's why they're called voltaic or galvanic. We'll talk about what voltage is, something called standard reduction potential, and standard cell potentials. Again, a cell is just a battery. So when we're talking about the standard cell or the standard potential, we're talking about how many volts can this battery produce. Alright, so first off, let's just talk about what current is. Electric current is the amount of charge that passes through an area per second. Okay, so if you think about having a wire, okay, so we have a wire here. The amount of current would be, if we just took a cross section, like right here in the wire, and we counted how much charge came through that spot right there per second. Okay, that would be the current. So the charge is signified by Q and measured in coulombs. And the abbreviation for coulombs is C. Time is measured in seconds here. So if we have minutes or hours or something, we'll have to transfer those to seconds. And then our current has a unit of amperes. One semi-confusing thing to me in this section is all of the different variables because their letters don't seem to match. So we'll have to memorize current is I in the equation, but its unit is amperes, A. Charge is Q in the equation, and its unit is coulombs. And then time is T, we got that one, and its unit is second. One really important factor that we need to look at here is what is a coulomb in relation to chemistry. So when we talk about a coulomb, that's the amount of charge, and remember charge is electrons. So 96,500 coulombs is equal to 1 mole of electrons. Okay, so it's kind of the electrician's way of talking about electrons. If 1 mole of electrons comes by, that's 96,500 coulombs. We're going to use this as a conversion factor very often in this course, and it's known as Faraday's constant. This number will be given to you on the AP sheet, the equation sheet, but it's usually just written Faraday's constant equals 96,500 coulombs. So you've got to know that this is a conversion factor for 1 mole of electrons. And we'll look at that and point it out on the equation sheet. So remind me to do that. Alright, here's an example question that we could use this equation for current. How much charge passes through the cross section of a wire that is carrying 0.987 amps of current for 12.3 minutes? So that amps is my I, my current, which is equal to the charge that passes through in a given amount of time. So if we want to solve, there's our amps for I. We're looking for charge, which is this Q, and remember it has the unit C for coulombs. And then this is our time, but we'll have to change it to seconds. So So how do we change minutes into seconds? So we'll multiply that by 60 to change that into seconds. All right, once we find the charge, the coulombs, they're then asking how many moles of electrons that is. So we saw in the previous slide that conversion factor between coulombs and electrons. So we'll use that to make that transfer. All right, so first we're going to change minutes into seconds by multiplying by 60. And then they're using their amps to go to coulombs. Now, another thing to note is that an amp, A, is the same thing as a coulomb per second. So you can also use amps as a conversion factor. So there's our amps, but they just made them coulombs over seconds so that you can see the seconds cancel and the minutes cancel, and then we're left with coulombs. If you think about the way that we had it set up, we had I equals Q over T. So how would you solve for Q? Well, you would multiply, right? I and T. So that's all they're doing here is they're multiplying. They're just not showing it in the same setup that we might use. But they're doing a good job of showing us how these units cancel, because an amp is a coulomb per second. So instead of putting A as the unit, they put coulombs per second. So you can see the seconds canceling. All right, so there's our coulombs. The question next is how many moles of electrons is that? And remember that 96,500 coulombs equals 1 mole of electrons. So we'll use that as a conversion factor. We need the electrons on the top because that's what we're looking for, and the coulombs on the bottom. So 96,500 coulombs is 1 mole of electrons. Now our coulombs cancel. We'll divide, and we see that that's less than a mole of electrons. Now, how would you figure out how many electrons that is? Not moles, but just how many electrons. Well, there you could use Avogadro's number, and remember that 1 mole of anything is equal to, and you put the Avogadro's number on the top so that mole would cancel, 6.02 times 10 to the 23rd. Okay, they didn't ask us to do that, but that's often a question. So if you have moles, you just multiply by Avogadro's number and cancel the moles to change it to just electrons. All right. Electrochemistry is driven by redox reactions, which we talked about previously. So remember, a redox reaction is a reaction in which we have an electron being gained and an electron being lost, someone being reduced and someone else or some other species being oxidized. So redox reactions involve electron transfer. In this example, we see they're calling this spontaneous or thermodynamically favorable redox reaction. So if you take a piece of zinc and put it into a solution that has copper in it, remember this AQ means aqueous, and the blue color is a clue that there's copper in there, this will react. The copper will form copper solid, while the zinc solid will form zinc ions. So the zinc is going from zinc solid to zinc plus 2. That's a loss of electrons, while the copper goes from plus 2 to copper solid. That's gaining 2 electrons. And you can see that happening. They're showing us that kind of zoomed in here. So this zinc solid is giving 2 of its electrons to this copper ion. That copper ion is becoming copper solid, so it'll kind of land right there. And then the zinc is becoming a zinc ion, so it'll go out into the solution. So they're just transferring their electrons. So there you strip, and then the zinc is out in the solution. And this will happen over and over again until you have copper solid and no more zinc. Alright, this slide is kind of giving us a clue for when we're on the AP exam. If you see a reaction in which you have a solid metal and it's put in a solution where there are metal ions, it's going to be this type of redox reaction. So the example they're giving us is a copper penny dropped into a solution of silver fluoride. Well, we have the copper solid, and then the silver fluoride gives us that silver ion. The fluoride is likely a spectator because it's soluble with silver and also soluble with copper. So our reaction would be the copper solid, the penny, reacting with the silver ions. The silver ions have a positive charge and the copper has no charge. The copper is the solid. The solid is going to give an electron to the silver to make silver solid and copper ions. Now, how many electrons it gives away depends on what charge copper wants to have. And copper is normally going to prefer to be +2. So it needs to get rid of 2 electrons. So another silver ion would likely come along and take a second electron from that copper. So we'll probably see copper and 2 Ag. Okay, we'll see how it plays out here. So the copper goes to +2, so it lost 2 electrons, and the silver gained an electron to go to silver solid. We need to balance that because the copper lost 2 electrons, right, to get to +2, but the silver only gained 1. So like I said before, there would be 2 silver ions that would come up to the copper to get those electrons, and that would form 2 atoms of silver solid, or 2 moles if we're talking on a larger scale. Alright, so that is an example, 2 examples really. We saw the copper and the zinc, and the silver and the copper, where we have electrons being transferred. However, that doesn't create electricity because the electrons, if we look back, they're just moving right there, right? Just right straight from the zinc to the copper. So that's not helping us create electricity in any way because the electrons aren't really flowing. So what we can do is create a device that transfers those electrons through a pathway. So instead of the zinc coming up and touching the copper in what we call a direct transfer, we're going to force those electrons to move through a pathway if they want to get from one place to the other. And those electrons moving through that pathway is electricity, and this device that we're going to create is called a galvanic cell. Now, a galvanic cell with these electrons flowing, it is always thermodynamically favorable. Okay, that's what this term right here, whenever we see spontaneous, we want to remember from the previous chapter. See if I can put it here for you. Thermodynamically favorable. Okay, and recall what that means. If these are thermodynamically favorable, what does that tell us about their delta G value? Well, that means that their delta G value has got to be less than 0 or negative for it to be thermodynamically favorable. From the last chapter, what does that tell us about their K value, their equilibrium constant? We know that it's got to be greater than 1 since these are thermodynamically favorable. So galvanic cells, also called voltaic cells, these are cells in which we're producing electricity spontaneously or favorably. We take chemical energy that's stored in the system and we're going to convert it into electrical energy to move those electrons. Right, so let's see what this looks like. Here's an example of a classic galvanic cell. If you Google galvanic cell, this will pop up. Okay, this is the most popular galvanic cell, the zinc copper cell. It even has its own name. It's called a Daniell cell. So galvanic cells can be made with any combination of metals, but this one is just used a lot for example. So we have zinc in both the solid and the ion form, and we have copper in both the solid and the ion form. Now recall from our first example that it's the zinc solid that was losing the electrons and the copper ion was gaining them. So here's that same exact reaction up here. So the zinc over here on your left is losing electrons. Those electrons are leaving the zinc. The copper ion down here in solution is gaining those electrons as they travel through this piece of metal, and that's forming copper solid. So all we've done is we've taken the zinc and copper reactants that we had previously and we've separated them and now connected them with a wire. So those electrons have no choice but to flow through the wire to get to the other reactant, and as they do so, that is electricity. So you see this light bulb here is lighting up because of that flow of electrons. So we have, in essence, produced electricity. Now, there's a lot going on here, so we'll kind of take it piece by piece. Over here on the left, you have the zinc losing electrons. So we say it's being oxidized. And you have the half reaction going on down here. So on this side, the zinc solid is losing electrons to become zinc plus 2. Those 2 electrons are leaving and going to the other side. Over here, we have the copper ion being reduced to form the copper solid. So those electrons are coming in to make that happen. So that's the reduction. The side that oxidation occurs on is always called the anode. And the side that reduction occurs on is always called the cathode. So you can remember anode and oxidation, those start with vowels. And then RC, like RC Cola or RC car. Okay, RC. Reduction happens at the cathode. The electrons always move from the anode to the cathode. So they always go anode to cathode. Okay, alphabetical order, those electrons move. There's one more important piece in here, and we'll talk about all these things in more detail. We're just getting a good overview right now. That is the salt bridge. As the electrons flow, you're going to have a unequal distribution of charge. So the negative is moving over here to the right-hand side, and as soon as you get an uneven distribution of charge, the electrons won't flow. So if you don't have some way to balance your charge back out, the cell or the battery will not work because the electrons won't flow if there is uneven charge. So this salt bridge allows the charge to stay balanced. So as those negative electrons move from the left to the right, the salt bridge will send negative ions in to replace that lost negative charge. So in the salt bridge, in this one, we have sodium sulfate. It can be any ionic compound. It will send ions to balance the charge. So wherever the electrons are leaving from, you'll send a negative ion that way. And then where the electrons are coming, there's going to be too much negative charge, so we'll send some positive charge over there to balance. All right, so the way that you can keep up with this is the negative is called the anion, right? So the anions flow toward the anode, and the cations, the positively charged ones, flow through the cathode. The electrons do not come through this salt bridge. It's just ions. The electrons move through the wire to produce that electricity. Right, here is a more zoomed in picture of what is taking place at what we call the electrodes. We have the anode where the oxidation takes place. The zinc is losing 2 electrons, and as it does, it falls off into the solution. Those electrons move through the wire to the cathode. They move through the copper solid metal, and then the copper ion in solution picks up those 2 electrons to become copper solid, and it's sticking to the cathode. So the anode is losing solid, it's dissolving into the solution. The cathode is gaining solid. So the anode, this strip of metal, will actually become lighter, smaller, as the ions move into the water, whereas the cathode, if you weighed it before and after, it would be heavier because the ions are moving out of the water onto the cathode. The salt bridge. Okay, let's talk a little bit more specifically about what this is. A salt bridge can be a complicated apparatus, or it can be really, really simple. So we'll talk about the one that you would use if you had like fancy material first. It would be a U-shaped glass tube with a solution of gel in there, and in that gel you would have these ions, and the ions could move. The cations could move toward the cathode to replace that lost, to combat those electrons that are coming in, and then the anions would go toward the anode. These are some popular cations and anions that are commonly used. Okay, it's called a salt bridge because a salt is an ionic compound, so it has cations and anions. You got to have both. The ions do not react. If you have ions that are reacting on either side, you have a problem. Okay, you picked the wrong salt bridge. So if you see some reaction occurring on one side or the other of your galvanic cell, then we've got the wrong ions. Sodium is a good one to use because it's usually soluble and non-reactive, and then nitrate is also a good one because we know all nitrates are soluble. Sulfate can get you in trouble if you have something that it forms a precipitate with. So I usually try to stick to like sodium nitrate or potassium nitrate. So ions from the salt bridge, again on this third point, they must not react to form a precipitate. Okay, that's going to cause a problem if they do. What is their purpose? They're keeping the solution neutral. Okay, this is often a question like a free response style question, and this is your answer. The ions are keeping the solutions neutral. If those solutions do not remain neutral, the reaction will stop. So if there's no salt bridge, there's no flow of electrons. There's no reaction. So we need the salt bridge. So the salt bridge could be this U-shaped tube. The salt bridge can also be just a piece of paper that's been soaked in salt water. And you can just drape it across the two solutions and make sure it gets into the water. And then those ions can flow as long as that paper stays wet. They can flow through the water on the paper. So it can be very simple. It doesn't have to be something complicated. All right, here's a zoomed in picture of the salt bridge. So in the salt bridge, your anions could be nitrate, sulfate, chloride, whatever you have. So in this case, they use sulfate. They're going to flow toward the anode because they're negative, and on the anode the electrons are leaving the anode, so negative's leaving, so we need more negative to come in to balance. The cations, or the positively charged species, they move toward the cathode because electrons are coming in to the cathode, so that's increasing our negative charge. So we need positive cations to come in and help balance that solution. All right, the electrons, remember, they flow from the anode to the cathode always. Why do they do that? It's the same reason a ball rolls down a hill. Okay, electrons flow from the anode to the cathode, the same reason a ball rolls down a hill. The potential energy for electrons is higher at the anode and lower at the cathode. And all things naturally move to a lower potential energy. So you can imagine the anode at the top of the hill, the cathode at the bottom of the hill. So the electrons are just rolling down to the cathode. All right? So here you see the rock. If you drop a rock, it's naturally going to go down due to gravity. If you wanted to bring it back up, that would require work, okay, based on the weight of the rock or the mass of the rock and the force of gravity. The same thing is true in a voltaic cell. However, it's not gravity that's doing the work, okay? It's the voltage that we talk about in the work, okay? And the voltage is the potential difference between the anode and the cathode. It's how big is the hill. So in some cells, the hill is really small, so the electrons are just moving a little ways, right? Not actual distance, but in terms of energy, there's a little change in energy, and so there's not much voltage being produced. But in some cells, there's a big change in the potential difference or the voltage, and so we get a lot of energy being produced there. Okay, so you have your anode with its potential energy and your cathode with its potential energy, and then you have your wire and your electrons flow from the anode to the cathode. Now, again, the electrons are not actually flowing down, like down to the ground. Okay, this is an analogy. The anode is at a higher energy than the cathode, so the electrons flow from the anode to the cathode. Now, depending on how far apart in energy these are, is how many volts we can get out of the system. Okay, and it's also how many volts we would have to put in if we wanted to move those electrons back up. So if you think about using a battery, in a battery it has an anode and a cathode inside the battery. And when you connect the anode and the cathode of that battery by putting it in a device, the electrons are flowing from the anode to the cathode. And that's the electricity that you're using in your device. However, if you want to recharge your battery, if you have rechargeable battery, you're going to hook that up to the wall, and you're going to use the voltage from the wall to move those electrons back up. Once they're back up there, they can flow back down, and then back up and back down and back up, depending on if you're recharging your battery or not. Okay? Does that make sense? If you have an anode and a cathode that aren't very far apart in energy, and we'll look at how you tell, but you're not going to get much voltage out of that system. Okay? Please jot down any questions you have about this. This is a very important concept. Alright, so summary of what we've seen so far. The energy is the difference in potential energy between the anode and the cathode. The charge that we're talking about are electrons. And each electron carries a certain number of coulombs. Because remember, 96,500 coulombs is 1 mole of electrons. So this, what they're saying right here about electrons and coulombs, okay, that's just a conversion that they got from Faraday's constant. So don't worry about these numbers here. Let's go down to this fourth point. If we have a 12-volt battery, then that means that the potential difference between the anode and the cathode is 12 joules per coulomb. Okay, that's what volts are. Joules, that's a unit of energy, per coulomb, that's a unit of charge. Okay, and we won't worry about these specific numbers here. Right? So the key that we've learned so far is what is the anode, what is the cathode, what's happening at each one, why are the electrons moving from the anode to the cathode, and then when we say voltage, what does that mean? Okay, that's a difference in potential energy between the anode and the cathode.